It's
yeah.
mine. Okay. If during my talk somebody will formulate questions, don't hesitate to raise your hand. Okay, but I start because we're out of time. First of all, let me thank again Professor Dabramov for his very interesting paper. All papers certainly are very interesting. And I took the opportunity to ask questions which I could not pose during his talk. And we already said about his reasoning, Professor Abramov. It seems to me that it based very much on the electromagnetic theory, on the existence of electromagnetic radiation. But if you suppose, for example, that you have the decay of strong interaction particles, so one particle decays due to strong interactions without participation of electromagnetism, how in this case your argument can be applied? This is my question to Professor Dabramov, if he is here.
Yes, it's a nice and tricky question. Thank you. And well, let me understand if I properly understood your question. You are asking if my derivation, namely the general one, let's say in this way, is applicable to a decay in which also particles are emitted, right? Is it correct?
Yes, switch off electromagnetism, switch off. What's happened?
Both radiation and particles, okay. Yes, okay. Well, I think that for what concern the particles emitted by during the emission process, I think that the general mass energy equivalence relationship would also apply, but I am afraid that it applies in the less interesting way, namely like in the example I made during my talk, my presentation. I believe that in that case the general mass energy relationship will give simply the mass of the particles. Only the mass of the particle, like in the simple classical example in which a parent body, classically emits masses with non-relativistic velocity. I believe that it should work like this, and this the general mass energy relationship that I showed you before. I think it gets interesting only when it is applied to emission in the form of electromagnetic radiation. In this case, it transforms. It actually transforms in a proper mass energy equivalence, because radiation can mass necessarily transforms into radiations. But if during the emission there is also the production of particles, which is massive bodies, in that case, that relation will give, I assume, I don't know, I must think about that, but I assume that I guess that the mass energy relationship, the general mass energy relationship, should simply give the mass of the particle.
Yes.
In the balance, in the energy balance of the process.
Yeah, but if, for example, we try to apply your arguments or maybe other arguments to the case of the absolutely stable particle. So let's take the proton. How do we should we argue in order to prove the mass energy relation for such a particle which is absolutely stable?
Well, very difficult question, and I must confess that I should think about that. I do not have a short answer to your question.
Okay, so we have more questions to you, I see.
Okay.
Please. Gia, go ahead.
Yeah, my question is to Professor Aristarchou, not to Professor D'Abramo.
I'm here.
Hello?
Hello,
Yeah.
I'm here.
Yeah, I'm trying to understand this chain of statements. So
Mhm.
we postulate that commutator of the momentum and the coordinate operators is IH. From there, we can derive via Kennard and Robertson that the product of the dispersions is bigger than H over 2.
Exactly. Mhm.
And from there, we are saying that this is another realization of the statement that if two operators do not commute, then the corresponding eigenvalues, two eigenvalues cannot be measured with the zero dispersion.
Could you please repeat the last portion?
So if I start from the non-commutative operators, then I
Uh-huh.
can derive the Heisenberg relation for the dispersions.
Definitely. Mhm.
And I can, since these p's and x's are interpreted as a possibly observable coordinated momentum, I am saying that from here I am deriving that the product of dispersions of the measured physical quantities coordinated momentum is bigger than h over 2. So what the Bohmian mechanics changes in this chain of statements? Does it changes the commutator relations? Because if I start from commutator relations, I think that I am simply immediately deriving delta p delta q bigger than h over 2, and there is no way around it.
Definitely, yes. As I said, this is just a mathematical fact, and this is no way around it, as you are saying, yes. The thing is, the operators have no fundamental significance in Bohmian mechanics. As you said, as you maybe saw in my short introduction, I haven't mentioned operators whatsoever, and the significance of the relation, this delta q delta p is larger than h bar, of course, the empirical input, of course, remains the same. It means in standard quantum mechanics means nothing more than what I said, is that if you do two sets of measurements, particular measurements on two large ensembles, you have then distributions which have certain width, and if you have if you take a product of those width, then it cannot be smaller than a certain number. And it is exactly the same in Bohmian mechanics.
Okay, so the commutator is also same as in quantum mechanics. There is no change in the formalism. That's what I was trying to find out.
I would say that the formalism, when you formulate Bohmian mechanics, you don't need operators at all. And operators come about only if you may show that operators are a nice bookkeeping device. So if you then ask, what is the, let's say, you do position measurement, yes?
Mm-hmm.
And you ask them, according to Bohmian mechanics, what is the prediction of the position measurement? What is going to be the distribution of the position that I find? The answer is going to be Born's rule. Then, of course, if you ask what is the mean value of what is the mean of the positions, then you may argue that in order to find it, you can use an operator. But since the Born's rule is correct, so it means that also the mathematics that you usually use in a standard formalism is also correct. Now, you may also ask, what is you do the usual momentum measurement, which is usually a measurement of velocity in scattering regime. Yes, for example, it's usually done via time of arrival, actually, or via curvature of the trajectory in the bubble chamber. And you may ask, what's the distribution according to Bohmian mechanics? And you may actually show that it happens so that using the momentum operator, namely the derivative, you may get the momenta of the distribution. I meant now the expectation value and the divergence and so on. These are derivable things. Operators do not play fundamental role.
Okay, all right. So quick follow-up question, because I'm not quite sure that I understand what do we call by the Born's rule.
Yeah. By the Born's law, I mean the following. It's the statement that the probability to find a particle in a certain region of space I'm now talking about, for simplicity, one particle system, is given by the integral over this region of psi squared.
Okay, probabilistic interpretation, understood. Thank
Exactly.
you.
Oh, yeah, thank you for the question.
Okay, so I take the opportunity that Serge is still here, and I will ask him one more question. Not a question, maybe. I'm a little bit lost with terminology, maybe.
Yeah.
We call Heisenberg uncertainty principle. When I say principle, for example, if I take the relativity principle, I take it as a starting point, and I can derive from this relativity principle everything which constitutes what we call the theory of relativity.
Mhm.
If I take instead the Heisenberg uncertainty relation,
Mhm.
I don't know, if I start with that, I have nothing more. If I can, with logical derivation or reasoning, to derive something more than this uncertainty relation. And also, it seems to me that why people call this principle, because this relationship between uncertainties is to be derived. If you know the commutational relation, so we can derive this principle just mathematically. And so this is not a principle, this is a result of more general propositions.
Yes, this is an excellent comment and very to the point. In fact, in the literature, there is a mess of it, just a mess, what people call principle, what people call the relation, and so on. And I tried to spare time. But if I had more time, during my talk, I would have said that referring to uncertainty principle, I personally mean the whole bunch of the collection of Heisenberg's arguments together with his uncertainty relation. So I just need a shortcut to say that it's not only the uncertainty relation, but also certain analysis which comes together with it. So I would say it's my own term. In the beginning of my presentation, when I was saying uncertainty principle, I meant exactly that. So whatever comes together with uncertainty relation.
With wave functions, with Hamiltonians, with all.
Not exactly that, but some, when you have just uncertainty relation, it doesn't have any, it's not clear what fundamental significance it has, because it's clear what empirical input it has, yes, and I repeated already twice, but it's not clear why is it so important. And that's why at least some talk is also needed after that. For example, Heisenberg spent a lot of time saying why the consequence of that is that there is a null trajectory, so why this is a matter of personal belief. Some people in some lectures are saying, well, the particle that I didn't mention, but people are saying the particle is actually a wave, so a wave-like thing. So if we can ascribe a position to it because it's like a narrow wave packet, then we cannot ascribe momentum. So there is always some talk around it. And referring to uncertainty principle, I meant uncertainty relation plus this talk. But it is not it's not the generally accepted term. So in general, people usually use uncertainty principle as a synonym to uncertainty relation. And this is a kind of a mess there. And I would say that your objections are very to the point, and people should not do that, because people should speak of uncertainty relation and just forget the term uncertainty principle.
Well, maybe I would call it principle because it was derived before all the computational relations were there. So it was suggested, sorry, wrong word, not derived. It was suggested as something based on purely physical, experimental, observational considerations. So computational relations is just one of mathematical relations to derive, if you want to derive the principle. But he came up as an empirical fact, which he put in the, I don't know, in the ground as a ground stone of quantum mechanics. So it's terminological thing. I just wanted to make a quick comment.
Yeah.
So just maybe to make things more or less finally clear, let me ask you, are there uncertainty relations ontic or epistemic?
Are the uncertainty relations ontic or epistemic?
Yes.
Which one? You mean this one? That
Second one more corresponds to your description of what you understand under the principle of uncertainty relations. Okay.
Wait. Let's repeat. So you are saying you are now speaking of several uncertainty relations. Which one is the first? Which one is the second?
Uncertainty relations. Let's take it now. Let's qualify them in terms of ontology or epistemology.
Yeah. Okay. Let's take the one that I was. So the one that we know from the textbooks. Yes. So
Yes.
this delta P, delta Q, and so on.
Yeah.
I wouldn't even say it's neither this or that. It's neither. It's just about the results of experiments. It just it is not. It's definitely not ontic. Yes. It's not about. It's not about if
And I understand, but I think that's why I have chosen the second option. You say that it's not.
It's definitely not ontic, but I also wouldn't really say it's epistemological because
Okay.
because look, because it's not it's just there are certain laboratory operations that we do which we call position measurement and momentum measurement, and it's just known that the distribution that we get have certain property, and this property is given by this relation, and I think this is all to it.
Okay, cannot be qualified in terms of this notion.
Yes. Mm-hmm.
Thank you very much. I'm not sure that the audience is very much appreciate this language. Okay, thank you. Thank you. I want now
Thank
to
you.
go further. We cannot skip the second speaker. I mean, Boris Zetic is here. Boris?
Yes, I'm here.
Oh, very good. Now let's ask people what they have to ask you about your talk and your ideas. Still nobody, and so I have to. It's my duty to ask. So my question is as follows: when you take the curved space, momentum space, we know that the curvature of the coordinate space is due to some kind of general relativity principle according to which the distribution of matter change the metric or says to metrics what to be. If there is something similar in the momentum space, for example, if you have nothing, you have just the Minkowski space in momenta, but if you introduce some idea, I don't know which one, but similar, and you will have as a solution of such kind of equation now already the curved momentum.
Well, actually, there is that thing, and that's this Fock's approach to hydrogen atom. So there is this strange symmetry of the hydrogen atom. So the azimuthal symmetry, right? So the question is, where does this symmetry come from? We don't see it in a coordinate space. So Fock actually showed that the problem of hydrogen atom when projected on the momentum in momentum representation actually corresponds to motion of a free curved momentum space on actually constant curvature momentum space. So this is also one approach. One can also think about the possibility that the curvature of the momentum space is somehow generated by some fundamental interactions.
Mm-hmm. Okay, and the second question is as follows. You try to construct the quantum field theory with these premises about the curved space and so on, and you have the scale P, large P, scale which can be sent to infinity or well. Now, you say that with this P finite, you obtain finite field theory without divergences, okay? Now, let's imagine that you manage to construct some scattering amplitude, for example, with that, which is finite, depend on energy, on transverse momentum, on angles and everything. Okay, now we take the same theory for example, 5 to 4, which is treated in the usual way, which normalization, etc. They also can obtain the finite amplitude. Now, if I send your P to infinity, if I will recover the normal finite amplitude which we obtained with usual ways.
Well, the answer is yes, short yes. So it's like asking me if you start with the sphere and if you send its radius to infinity, will you get the plane? Well, the answer is yes, you will get the plane. It will not have curvature anymore. It will become flat. So up to some boundary conditions at infinity, but we we don't worry about those.
Also, it was for me, the last question to you, for me at least. I was very much, I wonder, because you have said that you are going to use this in statistical physics, but how to deal with in statistical physics with such huge scale as you described P near the Planck mass?
So it just appears as another parameter in the, so always, whatever you do, there is always this consistency condition. So any result that you get,
Forever. You choose for any problem its own P.
No, you sort of take it as it's a universal fundamental constant. But the fact of the matter is, whatever you do, your result will always be the standard canonical result in whatever you do, times in the bracket, then comes 1, then comes plus, and then comes some typical energy or momentum of the processes that you are looking at, divided with this capital P, with this constant. So you will always.
In low energy domain, it seems that this P should not play any role at all.
Of course, when you are low in energy, it doesn't. This is the problem with this research. It could be. I mean, I could die before we are able to reach experimentally any energies where any any sign.
Everything fits in. Okay, thank you. So let's go further. If no more questions to Boris. We shall go to whom? To Serge. Is he still here? Aristarchov, Serge. No.
Yes. Sorry, I couldn't unmute myself.
One thing I'd like to ask you, because if I remember well, maybe you also have read that. In one of the books, the crazy book by Karl Popper, he wrote something about violation of the uncertainty principle. Can you comment on that?
Let me recall, because I also read Popper and mentioned him in the paper.
Exactly, it was some book devoted to quantum mechanics, or bear the quantum mechanics in the title. Okay, but if you don't remember, don't mind.
Wait, but I can comment on that. So what I wrote was not about the violation, but I still can comment on about the violation in general, because Popper was, I'm sure he did write something about the violation of the uncertainty principle, and I think also Ballantyne wrote something about it, and many other people. The thing is, one has to be again very clear about what one means by uncertainty relation or uncertainty principle, and as we have already discussed with you, this delta P times delta Q is just a mathematical fact that is larger than H bar. So, and also what it means empirically is also clear. So you may do whatever you want, you're not going to break it. It's just how it is. If you do these laboratory operations, get two distributions, and you multiply their width, you will never get something smaller than H bar, period. But people have noticed that also that Heisenberg actually aimed at something different. Yes. So,
yes, it seems to be. Is it from the point of physics, for example, such conclusions should be judged erroneous? No.
which conclusions?
A conclusion about violation or possible violation of the uncertainty relation.
If one says that he or she can violate the uncertainty relation as it was presented by Kennard, and if one understands by that exactly what, I mean, empirically what it is, then it's going that then it's nonsense. But the thing is that Heisenberg himself also just used this relation to argue for something else. Yes, he was not talking about, as I was saying, discussing the gamma microscope experiment. He was not talking about repetitive measurements on two ensembles. He was talking about simultaneous measurements of position and momentum.
Yeah.
In
No.
every time. And this is something, and then he was multiplying the accuracy of the with which you can determine position and the inaccuracy of the disturbance of momentum that the position measurement introduces. And these are actually the quantities for him. They, as I was saying, they were equivalent to this delta P and delta Q. But this point is harshly criticized in the literature by many authors. And there, in principle, you may this which I called epsilon Q times epsilon delta P larger than H bar. This you can violate.
Okay, thank you. It's very instructive. And the last thing I would like to ask you. You dealt, and not only you, with point-like particles. But what can we say about all this subject? If we take, for example, the proton, how can we say it has its own proper size? How the proper sizes can change anything which is related to the uncertainty relation? Just uncertainty, even the very uncertainty of the coordinate, for example.
If we take one of the empirically adequate trajectory containing quantum theories,
we take physical non-point-like particles. They have all the sizes.
Let me put it as follows. So the trajectory containing quantum theories that I know of do not deal with the non-point-like particles. Yes.
Yes.
They
with namely. When people derive or argue about uncertainty relations, I never met that they took into account the sizes of the particles. They maybe silently suppose that they deal with point-like particles that are distances where the proper sizes are not very important. But they are. For example, the size of the proton is 0.A Fermi. It's not negligible thing. And how to account it in this resonance?
Okay, let me put it as follows. In my opinion, the uncertainty relation doesn't put any constraints on the size of the particles.
No, but which coordinate you mean? Center of mass coordinate or else?
It doesn't matter. It just doesn't put any constraints. It doesn't matter what you mean as a size.
In this case, the size of the particle should enter the uncertainty. No, it should figure as a parameter.
In which case? Which case do you consider?
If you try to argue about uncertainty of the position of the proton, for example, the proton has its own size, 0.8 Fermi. In this case, if we apply the Heisenberg, it has nothing to say about its size, but it should, I think. It's impossible because this limits the accuracy with which we can measure even the position of the center of mass of the proton, what that means.
Yeah, now I understood. So I'll try to rephrase and you tell me if I understood correctly. So you're saying that the proper sizes of the particles also limit our accuracy of determination of their position.
Yes, sure.
Well, they're definitely so. Yeah, you are absolutely right. But I just don't think that uncertainty principle has anything to do with it.
Okay, but the problem remains. Okay, that's good. That's
Yeah.
There's things to think about. Okay, thank you very much. So
Thank you for the question.
for you, now we would like to talk about the presentation by Chao Song. If Chao Song can join us.
Yes, I'm here.
Okay, it's not too late in China, no? It's okay. You should, or vice versa. Or it's too late, no? Okay, anyway, independently of time, I have to ask people in the audience to ask you the questions they want to ask you concerning your arguments and your theory and so on. Please. So if somebody else in the audience, no, I don't see. No, no. Oh, so it's my destiny to start maybe and to finish maybe. Okay, you argue about your theory of the ether, but certainly we know that in literature we can find several options of the ether which is applied to the theory of gravitational. For example, the anisotropic ether, etc., with definite. For example, there is some kind of so-called very special relativity where the rotation symmetry is violated and so on. And there's also there. What do you think about other theories of the ether which are made in literature?
Thank you. Yes, the concept of ether is a very old concept since the ancient Greece, ancient Greek. So the concept also in China, also in ancient Egypt, the concept of ether is very old in the history. Einstein abandoned the concept of ether in the years 1905 to 1916. However, Lorentz believed that general relativity could be reconciled with the concept of an ether at rest, and wrote a letter to Albert Einstein. Einstein changed his view later and introduced his new concept of ether. So I think for instance, Einstein and Infeld said matter is where the concentration of energy is great. So maybe Einstein also agree with the existence of an ether, as you have already said in your presentation, relativity theory, genesis and completion. You have so the I think that the ether theory is valuable for us to study, continue to study. Thank you.
Thank you. Also, I would like to ask about, because according to you, if I understand properly your talk, you insist that your ether is a classical liquid or something like that, plastic, not quantized.
Yes, the concept of ether, I think, is in my opinion, the concept of ether is changing, and For instance, the omega 1 for instance, the Lord Kelvin's ether is the electromagnetic ether. This ether is the medium of light and the electromagnetic wave. This ether is called the omega 1 substratum. And I think that omega 1 substratum is also subject to is also obey the quantum mechanics. So the ether concept of ether is not contradict with the with quantum mechanics, I think. And also the concept of ether is not contradict with special relativity. And the concept of ether is not contradict with the general theory of relativity, maybe. However, in vacuum mechanics, there are some differences between the VM and the GR. GR is the general theory of relativity. So I think the theory of ether is developing, I think.
Okay, thank you very much. Thank you very much. I think that we come to finish of the discussion session. Thank you very much, all participants and speakers of the last session. And let me come directly go to the closing address, so-called. And so what can I say about our conference? It is quite dense, 3 days. And I believe that it was generally very lucky because we could embrace almost all modern subjects which are very hot, starting from cosmology and gravitation and so on, and coming to quantum chromodynamics, both continuous and both lattice theory of QCD. And also we had 2 very interesting experimental talks. So we are in touch with experiment and heavy ions and the program of sources of other particles. And finally, today we had already discussions which were related to, in some part with history, in a lesser part with philosophy. That time maybe we had no philosophers among our speakers. We hope to do that maybe next time. And on behalf of the organizing committee, let me thank all participants very much for your taking part in this event. And you have made this event very interesting. This is not just a flattening to you, not it's true, because we have seen that even in the evening we have several people, several tens of people who take part. And this I want to say already maybe more concretely that we should inform you about the publication of your talks. And also I would like to warn discussion leaders that their summaries also are expected in the proceedings of this conference. Okay, I'm coming back to the closing address. Let me express my and my colleagues' deep gratitude to you for participating. Thank you very much. And till the next conference or next workshop in future, we hope the future will not be as deeply as now, and will be much more bright that we have now. Thank you very much, and bye-bye.